Okay, hi guys. Today we are going to look at the factors affecting resistance of a conductor in more detail, after which later I'll be doing a very quick summary of the entire chapter, and then after that we are going to do some work examples, alright? Okay, so basically you roughly know about this already. We've talked about this in the last lesson. Okay, so please turn to page 12 of your notes. Okay, so the resistance of a conductor depends on its length. So we say that R is directly proportional to length. Okay, so this is the symbol for directly proportional. Okay, so for those of you who want to copy this down, okay, you can just copy this down, right? Directly proportional, right? Okay, so what does directly proportional means? It means that as the length goes up, resistance goes up. As the length goes down, resistance goes down. Okay, so this is the meaning of directly proportional, alright? Okay, so for a shorter wire, okay, it will be of lower resistance. Lower resistance means there will be higher current passing through the wire. Okay, what about your longer wire? Your longer wire, since the length goes up, resistance goes up. So for a longer wire, the resistance will be higher. As the resistance is higher, what it means is that the current will be lower, right? So it will not it will resist more of the current, right? A higher resistance means it will resist more of the current, so the current value will be lower. Alright, so let's take a look at the next one. Okay, the next one is the cross-sectional area. So we say that the resistance and the cross-sectional area, they are inversely proportional, right? Because of this symbol, okay, this symbol, and then you have 1 over A. This means that resistance is inversely proportional. Okay, so you may want to write that down. Okay, inversely proportional. Alright, simply means, what does inversely proportional means? It means that when the area goes up, resistance comes down. When the area goes down, resistance goes up. Alright, so it means it's the opposite. When this one go up, this one come down. When this one go down, this one go up. Okay, so it's the opposite. Okay, so let's take a look at a thinner wire, right? So a thinner wire will have smaller cross-sectional area. Smaller cross-sectional area means the resistance will be larger. That means it will resist more of the current. It will make it more difficult for the current to flow through, right? So the current value will be lower. What about a thicker wire? So if it's a thicker wire, the cross-sectional area is higher, which means that the resistance is lower, right? Because it is bigger, it will not resist so much current. Okay, so it doesn't resist so much current. So the current will be, the resistance will be lower. Okay, so when the resistance is lower, then therefore it means that you can have more current flowing through, right? So you have a higher current which is able to flow through the circuit. Okay, so the third factor which is going to affect your resistance is the type of material. So the type of material is also referred to as the resistivity. So different materials can conduct electricity better than others. Okay, we know that copper definitely can conduct electricity better than iron due to its lower resistivity, right? So that's why most of your wires, okay, that it used are all made of copper. Alright, so this is a table to show you the different resistivity of the different materials. Okay, silver has the lowest resistivity, right? Which means that it allows more of the current to pass through, right? Lowest of the resistivity, while polythene has the highest or largest resistivity. Okay, so highest resistivity. Okay. So copper, you see, is not bad. Copper is actually, in this table, okay, copper is actually second. Okay, but of course, we don't make our wires out of silver because silver is very, very expensive. Okay, so we use copper to make our wires instead. Right? So, okay, so another common question that I get from students is, must they memorize this table? So the answer is no need to memorize. Okay, so you don't have to memorize. Okay, you just need to know that resistivity is dependent on the material. The lower resistivity means it allows more current. Okay. Okay, right. So at this point, just want to clarify that resistance depends on three things, right? So resistance actually depends on the resistivity, right? It depends on the length, and then it depends on the cross-sectional area, right? So if you have two conductors, right? One made up of copper and one made up of iron. Okay, let's say for example, this is iron. Same length, same area. Then of course copper wire will be lower resistance because the resistivity is lower, right? But if you change the length or you change the cross-sectional area, okay, then it doesn't necessarily mean that copper will have a lower resistance, because resistance will also depend on the length. It also depends on the cross-sectional area. So actually all these three factors, resistivity, length and area, is all linked to the resistance, and it is given by this formula, right? Okay, so actually must you remember this formula? Okay, the answer is no need. Okay, you don't have to remember this formula. Okay, in your syllabus, you are just required to know that resistance is directly proportional to length, which means as the length goes up, resistance goes up. As the length goes down, resistance comes down. Alright, and you also need to know that the resistance is inversely proportional to area, which means that as the area goes up, resistance comes down. As the area goes down, resistance goes up. Okay, so these are the two things that you need to know. Okay, but some students find that it is useful for them to remember this formula, okay, because it puts these two formulas into just one formula like that. So I leave it up to you, okay, whether or not you want to memorize or not. Okay. Okay, so next we're gonna take a look at the difference between open, close, and short circuit. Okay, so open circuit, you know what it means. Okay, simply means that the switch is open, current cannot flow through, and the light bulb will be off. Okay, in a closed circuit, what it means is that the switch is closed, the current can flow through, and the light bulb is on. Right? Okay, now this one is a little bit more tricky. So a short circuit means that the circuit is closed, the switch is closed, but what you have is you have a point whereby you have a very low resistance wire bypassing the light bulb like that. So when it bypasses the light bulb like that, the current will prefer to flow through this low resistance wire instead of the light bulb. So you have some current passing through the light bulb, but very, very little. Alright, so most of the current will prefer to flow through this wire of lower resistance, and that causes the light bulb not to be switched on. Right? Okay, so now let's take a look at a short simulation and as an example, okay, to demonstrate to you what I mean. Okay, so let's take a look at a simple simple example over here, simple simulation. Okay, you see that this is an open circuit, so the current is not able to flow through, right? Okay, so if I were to close the switch, right, you will see that the charges will flow around the circuit, right? So this is an example of a closed circuit. Okay, so then what does it mean then to have a short circuit? Okay, to have a short circuit means you have a wire of very low resistance which will be placed over here, right? So when you see this, can you see that what happens then is that the current will actually prefer to bypass the wire of lower resistance instead of through the light bulb. Right? Okay, and there you see you got, wow, got one fire like that, right? Okay, so this fire, what does it mean? Okay, because when you do this, it causes the circuit resistance to drop. A lot of current can flow through, and when there is too much current, what happens is that your circuit will actually overheat. Right? And when your circuit overheats, then it becomes dangerous, right? So that's why sometimes you hear people say, wow, short circuit caused the fire, the short circuit caused the fire. Okay, so now you know why. Okay, right. So now let's just do a very quick summary of the entire topic. So we've covered the topic. Yay, right? So this is not a very easy topic, okay, but I'm sure that if you do it step by step and if you are patient, you will be able to understand, okay, what's happening in this topic, all right? Okay, so we started off by talking about a circuit, right? So if you take a look, okay, you have a circuit and then the current actually flows from the positive to the negative, right? Okay, sorry, okay, let me just erase this first. Okay, so current will actually flow from positive terminal to negative terminal. So we say that this is the flow of the current, right? So even up to today, if we say current means flow from positive to negative. Okay, so what is this thing over here? Okay, this is only later on people realize that current is due to the flow of electrons. Okay, before that people didn't know. Alright, so people thought that current was due to the flow of charges that travel from the positive terminal to the negative terminal. But because we have been using it for so long, even up to now when we say current, we will use it as the flow of charges from positive to negative, right? So later on, people find out that A is actually due to the flow of electrons, and electrons actually flow from negative to positive. Okay, so if it's in your questions, when you see questions, when they ask for flow of current, be very careful. Are they asking for current or are they asking for flow of electrons? Okay. Alright, now then we talk about what exactly is current. So current is due to the flow of charges, right? Flow of charges, and current is actually equal to the charge divided by time, right? The rate of flow of charges, how fast the charges are moving. Okay, then next we talk about voltage, right? We say that before you can even have a current, you must have a voltage, right? And then that there are two types of voltages. One is the EMF. The other one is the potential difference. For EMF, it refers to the work done needed to push the charge around the whole circuit. For potential difference, it refers to the work done needed to push the unit charge through a component in the circuit, right? So EMF is referring to your batteries and your power source. Voltage is referring, potential difference is referring to the components in your circuit, okay, like your resistors and your light bulb and so on and so forth. Okay, but you see that the formula is roughly the same. Alright, so you just need to remember one only. Just remember, I will suggest that you remember this one. Okay, you can remember it as voltage equals to work done per unit charge. Alright, next one. Okay, the next one is the resistance. Okay, we know that the current in the circuit depends on two things. Okay, it depends on the voltage, it depends on the resistance. The more voltage there is, higher voltage current will be larger. Higher resistance, wow, then the current will be lower, right? So current will depend on these two things. So how is these three things combined into a formula? It is combined into this formula, R equal to V divided by I. Okay, resistance equal to voltage divided by the current. Okay, then we also talked about the resistance of a wire, right? And we say that for a wire, when the length increases, the resistance increases, right? So we say that when the length goes up, resistance goes up. When the length goes down, resistance comes down, right? Okay, then when we talk about resistance and cross-sectional area, we say that it is inversely proportional. Inversely proportional means opposite lah. Okay, when the area goes up, resistance comes down. When the area goes down, resistance goes up. Okay, so this is for the resistance of a wire. Okay, then we talked about a short circuit, right? So what is a short circuit? It is when you have a wire of low resistance and it bypasses the component in your circuit, right? So this wire of low resistance acts as a pathway for current to bypass the component in the circuit. So this can be dangerous since a large current flowing into the circuit may lead to high temperatures and may result in fire. Okay, then what else did we talk about? We talked about Ohm's law, right? Ohm's law. So in Ohm's law, what are we saying? We're saying that for a component, the voltage and the current passing through the component, if the voltage and the current passing through the component is directly proportional to each other. Directly proportional to each other means when I draw the V against I graph, or I draw the I against V graph like that, you will get a straight line that starts from 0. Then we say that these two components and conductors, they obey Ohm's law. What about conductors which look like that? Okay, so certain conductors, right, the voltage and the current, they are not directly proportional. So for this type of conductors, they do not actually obey Ohm's law, right? So conductors like this do not obey Ohm's law. Alright, so in terms of the summary of your notes, there you go, right? Okay, it's just these 7 points only that you need to remember for this chapter. Alright, okay, so remember these 7 points. Okay, the formulas. Okay, IQT, V equals to W over Q. Okay, R equals to V over I. When the length goes up, okay, I don't sing again lah. Okay, I think you're sian of hearing me singing already. Right? Okay, and then finally your Ohm's law over here. Right? Okay, so I hope this summary is clear for you. Okay, next I will go through some examples with you from example 13, 14, 15, 16, and 17, I think. Alright. Okay, so it will be good if at this point you can actually pause the video and then try the examples yourself first. Okay, so try it first, then after that, come back to the video and then try to see the answers, right, or the solution. Okay. Alright, so let's take a look at example number 13. So example number 13, a piece of constantan wire. Constantan is just a type of material, okay, of length 2 meters, has a resistance of 10 ohm. Okay, so what is the resistance of another piece of constantan wire? Alright, so normally for this question, right, what I will do is I will put all the information that I know first, right? So I will say that, okay, given, okay, this is what is given in the question. Okay, so given in the question is like that. Okay, the resistance is, okay, the resistance is 10 ohms, right? Okay, and then the length is 2 meters. Okay, and then the area, I don't know. Okay, so I don't know what the area is. I'm just going to put it as maybe area, I'll put it as X. Okay, because I don't know what the area is. Okay, then for part A, okay, you are given the resistance. You want to know what is the resistance of another piece of wire of the same thickness. Okay, so same thickness means the area got no change. Okay, no change in the area, right? But the length, okay, the length over here will now be 0.4 meters, right? So if there is no change in the area, it will not affect the resistance. So I don't need to care about the area, right, for this question. Okay, because there is no change in the resistance, the area doesn't change. But the length changes, right? So we know that resistance is directly proportional to the length, right? When the length goes up, resistance goes up. When the length goes down, resistance goes down. Okay, so because the length has decreased, so we know that the resistance value will also drop. Okay, but drop by how much, right? So we need to know first. So we take, okay, 2 and 0.4. 2 divided by what? Give you 0.4, right? So you realize that it's actually 2 divided by 5, right? 2 divided by 5 give you 0.4 meters. So this 10 ohm must also divide by 5. And then you will get that, 10 divided by 5 will give you 2 ohms, right? Okay, so that's your answer. That's it. Okay, so you can just say resistance equals to 2 ohms. Stop. Okay. Okay, what about this one? Okay, the next one, the resistance of another piece of wire of half the cross-sectional area and of length 0.8 meter, right? Okay, what I'm going to do is I'm going to start with the answer at A first. Okay, so I already know resistance, length, area. Okay, I already know that resistance is 2 ohms, when the length is 0.4 meters, when the cross-sectional area is X, right? So I don't know what X is, okay, so I just put it as an unknown value, okay. Okay, now for part B, what will happen to the resistance when you have half the cross-sectional area? Half means the cross-sectional area you have to divide by 2, right? So you have to divide by 2. So when you divide by 2 to the cross-sectional area, what happens to the resistance? So remember, resistance is inversely proportional to the area. When the area goes down, resistance goes up, right? So if the area divided by 2, then the resistance must times by 2, right? So R times 2 will give you a value of 4 ohms, right? Okay, so because the cross-sectional area changed, the resistance also changed, right? But it is not over yet because the length also changes, right? Okay, so the length also changes. So if the length changes, okay, if the length changes, then you also have to change the length and see how this affects the resistance. Okay, so for the first part over here, we don't change the length first, we change the area first, right? So we change the area first. Now, since the area has already changed, I want to change the length to see how this affects the resistance, right? So if the length increases by 2 times 2, then the resistance will also increase by 2 times. So what you get is you take 4 multiplied by 2 and then you get a value of 8 ohms, right? Okay, so you see that the final answer is like that. Okay, from the original resistance is 2 ohm, length is 0.4, area is X. What you do is the first step number 1, right? You change 1 first. So I decide to change the area, the resistance, or rather the length, I keep it to be the same, right? I don't change the length first. So I change the area first. So when I change the area, this one divided by 2 causes the resistance to increase by 2. So after that, what I do next is I now change the length. So the area over here, I don't change really, right? So when the length times by 2, the resistance also times by 2. So this is step number 2, right? And then finally, I find that my resistance value when the length is 0.8 meters and when the area is half of the original area, the resistance will be equals to 8 ohms. Okay, right. So now let's take a look at another example. Example number 14. Okay, so same thing. Okay, I'm going to do the same thing. Okay, so what do I know? What am I given at the start? Okay, so I'm given at the start that the resistance, okay, is 2.8 ohms. Okay, this is what is given to me. 2.8 ohm is the resistance. And then the length is 50 centimeters. Alright, and then the cross-sectional area is 1.00 millimeter square, right? Okay, now let's take a look at part A, right? So I want to do for part A. So in part A, the cross-sectional area remains the same. So yay, I don't need to do anything. Just write it down like that. Cross-sectional area remains the same. So it's not going to affect the resistance. Okay, because the area is the same, right? Okay, but the length is now 1 meters. Okay, 1 meters means this is 100 centimeters, right? So the length is now 100 centimeters. So because the length changes, right? So length times by 2, right? So when the length goes up, resistance goes up, right? So the resistance will times by 2. So this will give you a value of 5.6 ohm. Alright, that's it. Right? Okay, so that's it. Right? So the answer for A, resistance is equal to 5.6 ohms. Right? Okay, now let's take a look at part B over here. Okay, so in part B, the cross-sectional area is 2 millimeter square and the length is 1 meter, right? So we realize that this length of 1 meter is similar to the example in part A, right? So I'm going to use the resistance length area from part A. Okay, 5.6 ohms, 100 cm, 1 millimeter square. Okay, so I'm going to start with this. Okay, rather than the one given in the question, because the length is already at 100 cm. I know that the resistance is 5.6 ohm, right? Okay, so for part B, okay, I want the cross-sectional area to be, okay, let's take a look at the length first. Okay, length is 100 cm, right? For part B, right? Length is 100 cm also, okay, for part B. So no need to do anything to the resistance. Resistance will not change because the length doesn't change. But the area has now increased to 2 millimeter square, right? So there is an increase in the area by 2 times, right? So when the area goes up, resistance comes down, right? So your resistance will have to be divided by 2, right? And therefore you will get your answer to be 2.8 ohms. Okay, so for part B, the resistance is equal to 2.8 ohms. Okay, right, now let's take a look at example 15. Which of the following pieces has the highest resistance? So if you want it to have the highest resistance, then what you want is you want something where the length is the largest, right? Or the longest. Okay, you want something with the longest length, and you want something with the smallest cross-sectional area. Okay, smallest cross-sectional area. Oops, sorry. Okay, smallest cross-sectional area, right? Okay, so you want something like that. Okay, long one. Okay, long, thin one. Okay, highest resistance. Okay, so you will resist a lot of the current. Okay, so let's take a look at A, B, C, D. Okay, so which one has the longest length? This one already. Okay, this one has the longest length, right? And then which one has the smallest area? Smallest area is this one and this one, right? The diameter will, the diameter is the one over here, right? For cross-sectional area, this is the diameter. Okay, you know that when the diameter is smaller, the area will also be smaller, right? Okay, so you see that for C, this will be your answer, right? Pretty straightforward. Among the options A, B, C, D, this has the longest length. And then among the options A, B, C, D, B and C both have the smallest cross-sectional area. Okay, but because this length is longer, then therefore we say that C will have a higher resistance. Okay, right. Okay, now let's take a look at example 16. Okay, you have two lamps P and Q are connected in series with a battery. Okay, so put a battery there. Two lamps, okay, P and Q. Okay, they are connected in series, right? Okay, so let's call this P and let's call this Q, right? Okay, the work done by the battery in 0.6 seconds to drive a charge of 3 coulomb through the lamp P is 6 joules. So you need 6 joules of energy, right? Okay, so you need to do 6 work of energy, or the work done needed is 6 joules, right? And through lamp Q is 4.5 joules, right? So the work done needed to push the charge through lamp Q is only 4.5 joules, right? Okay, so you see that it requires more work to push the charge at P compared to Q, right? Okay, so first one, part 1, what is the potential difference across lamp P, right? So potential difference, what is the voltage lah? Okay, basically what is the voltage? Okay, so you have voltage, you have the work done, you have the charge, right? So you have the charge, this is 3 coulomb, you have the work done, and you want to find the voltage. So what formula comes to mind? V equal to W over Q, right? So the work done is 6 joules, the charge is 3 coulombs, and you will get an answer here of 2 volts. Okay, what about part 2? What is the voltage across lamp Q? Same thing, V equals to W over Q. Right? The work done, the energy required is 4.5 joules divided by 3 coulombs of charges. You get 1.5 volts. Okay? Okay, part B. What is the EMF of the battery? Also refer to voltage, right? So EMF is also refers to the voltage, but it is the voltage that the source provides, right? So this is the EMF, right? So you want to find out the EMF. So EMF is also equals to work done divided by charge. But remember, for EMF, you are interested in the work done needed to push the charge around the whole circuit. So if the charge requires 6 joules to go through P, and then 4.5 joules to go through Q, what is the total work done for this charge when it is pushed around the whole circuit? So the total work done will be 6 plus 4, right? Divide by the charge, which is 3 coulomb. So you will get your answer to be equals, 6 plus 4.5. Okay, my bad. Okay, so you get your answer to be 10.5 over 3. So this will give you a value of 3.5 volts. Okay, 3.5 volts, right? Some of you will already see already, you say that, oh, I noticed P is 2 volts. I noticed Q is 1.5 volts, so the EMF must be 3.5 lah. Okay, some of you can already see that, right? But that one we will cover in the next chapter. Okay, for this chapter, just remember, if you want to find the EMF, it is the work done for the whole circuit. So you must plus 6 joules plus 4.5. Okay, then we divide by the charge, which is going around the circuit, 3 coulomb. Okay, then you get 3.5 volts. Okay, and then for part C, okay, you want to find what is the current in the circuit, right? So the current in the circuit, the two formulas that come to your mind, okay, should be the R equals to V over I, or I equals to Q over T, right? IQT. Why does these two formula comes to mind? Because these two formulas has current in the formula, right? Okay, so let's take a look. What is it that you know? You know the time taken, 0.6 seconds. Okay, so you know the time taken is 0.6 seconds for the charge to flow through the whole circuit. You also know the charge to be 3 coulombs. Okay, you know charge is 3 coulomb. Okay, the total charge moving in 0.6 seconds is 3 coulomb. So immediately between these two formula, right, which one will you choose? Okay, so you choose the IQT, right, IQT. So the Q is 3 coulombs over the time of 0.6 seconds. So you will get a value of 3 divided by 0.6. Okay, so 3 divided by 0.6. Okay, you will get a value of 5 ampere. Okay, so this is for part C. Alamak, no more space already. Okay, then for part D, okay, calculate the resistance of lamp P and lamp Q, right? Okay, so for lamp P, you want to find the resistance. Resistance equal to voltage divided by current. Okay, so you already know that for lamp P, okay, this one, the voltage is 2 volts, right? 2 volts. And for the current flowing in the circuit is 5 ampere. Okay, so this current doesn't change. Okay, the current here, the current here, the current here, all is 5 ampere. Okay, this is the current flowing into the circuit, right? So you get 2 volts, divide by the current of 5 ampere. Okay, you will get your answer to be 0.4 ohm. Okay, 0.4 ohm. Okay, so this is for P. And then for Q, okay, what you want to do is you want to find, again, R equals to V over I, right? But this time around, the voltage, you know it to be 1.5 volts, okay, for Q. And you want to divide the current, which is also equals to 5 ampere, right? So 1.5 divided by 5 ampere, you will get a value of, if I'm not wrong, it's 0.3, right? Okay, 0.3. And since it's resistant, the answer will be ohm. Okay, 0.3 ohm. Okay, and then finally you have another question, last question in this work examples. Okay, remember this variable resistor, the one that we all tried out in class, right? When you slide the slider left and right, okay, when you slide the slider left and right, the resistance value will change, right? So how exactly does that work? Okay, because you notice that the current goes in here. Okay, then the current travels here, here. This is in a coil, right? So the current travels here and then out like that. Okay, the current travels here and out. So you realize that as you move this slider, right, the current will have to pass through a longer wire, right? So it will have to pass through a longer wire before it can finally go out like that. Okay. So explain how the resistance of the variable resistor changes as the slider is moved from left to right. Okay, so number one, we say that the resistance will increase, right? So why does the resistance will increase? Okay, because, okay, so we explain because, okay, the length of the wire increases, which leads to a higher resistance. Okay, so it's simply that, right? So a variable resistor works like that, okay, by adjusting the length of the wire in the circuit, right? By adjusting the length of the wire, what you do is you are able to adjust the current in the circuit. Okay, you can adjust the resistance and then you can adjust the current. Okay, so I hope you are able to follow. Please mark, all right, your work. All right, and I really hope you have tried first before you actually go and do this question. All right, okay, so mark. Okay, and then if there are any questions, please get back to any one of your teachers. Okay, we will be very happy to help you out. Okay, so take care, guys. All right, and yeah, I hope we get to see you guys soon. All right, bye bye.